one in our atomic structure and bonding unit, as we're going to be talking about today. So first things first, we were focusing more on the model of the atom that came out of Niels Bohr after Rutherford and those that came before it that made some advances towards this model of the atom. But looking at this model of the atom that Bohr was responsible for coming up with, based off the ideas of those before, basically he came up with the idea that the nucleus is in the middle and then there's different energy levels that are known distances away from the nucleus, and these are the only places that the electrons can actually orbit. Now, we're going to talk about in the next lesson kind of what is a little incorrect about this model, but for right now, we're going to focus on this one now, where electrons can only travel in these fixed spots, distance away from the nucleus. Okay, so looking at the next part here. So, electrons in the atom absorb a known amount of energy called quanta. So for example, this is the first energy level, okay? So the first one away from the nucleus, the second one away from the nucleus, third and fourth. It's just graphed a little differently, but you can just imagine it going out from the nucleus, and then again, first, second, third, fourth. These are the different energy values that you need to be at these different levels. So you'll see the first energy level has the lowest energy, so 0 eV is unit of energy. The second one, 1 eV, third, 3 eV, fourth, 6 eV. So what that's showing you is you have to have higher energy to be at the further electron shells away from the nucleus. So looking at this one here, the difference between the first and the second energy level is the difference of 1 electron volt. So if an electron were to get promoted from the first to the second, it would need to pick up 1 eV of energy, okay? So when you're talking about a known amount of energy they need to gain, it's a quanta, okay? And then when electrons gain this energy, they're promoted to a shell that's further away. This would be the excited state. So again, let's say an electron was promoted from the first energy level to the third energy level. It would have to gain 3 EVs in order to do that, and this would be its ground state where it was originally, and then this would be its excited state. Okay, and then eventually it's going to have to release that energy. It can't hold on to it forever. When it does release, it would fall back down to where it came from, in this case, the first energy level. So the energy difference between the shells are fixed, like I said before. When energy is released by the electrons, you can basically see that most of the time in form of light, and that's where we get this idea of electromagnetic radiation and a spectrum. So what you're going to see is that this is discovered using a spectroscope, and then each element creates a unique pattern. So you'll see hydrogen spectrum looks different than helium's, looks different than neon's and sodium's and mercury's and so forth. Okay, so this is a unique kind of fingerprint for each element. So if you were given a spectrum and you had kind of a key to line it up with, you would be able to figure out which element it is based off of what you have. Now, dealing with electromagnetic radiation, there's this idea that part of it acts as waves. So we need to be able to talk about some basic characteristics of waves before we move on here. So thinking about a wave here, so you'll see it down and up, so you've got peaks and troughs in here. Amplitude is how high it goes up from the middle. But what's going to really be important here is the wavelength. So that's the distance from a point on one wave to the exact same point on the next wave, okay? So you can measure that like from middle to middle, bottom to bottom, top to top, really wherever you want to, as long as you're being consistent, and it'll always be the same value. So that's the wavelength. The frequency is how often you see the waves. And then these are the two equations you're going to be using. So C equals lambda V. This is just a Greek letter. And then E equals HV. So C, everything's defined down here. But C is the speed of light. Lambda is the wavelength. It's generally in meters. V is frequency, which is measured in hertz, which may be a new unit for you. If it is, it's just seconds to the negative first. E is energy. H is this Planck's constant. It's always this value here. And then V, once again, is frequency. So frequency overlaps in both of these equations. Okay, so this is the electromagnetic spectrum that you probably have seen before in another science class. So when we talk about visible light in the spectrum that we create using spectroscopes, we're in this particular part of the spectrum, kind of right in the middle. But you'll see gamma, X-rays, ultraviolet, infrared microwaves, and radio waves are on here as well. The shortest wavelengths would be down here with the gamma rays, and then this is also the highest frequency. And then down here, longest wavelength with the radio waves and the lowest frequency. All right, so we need to be able to solve some problems using these equations here. So if you look in your notes here, I've got two examples for you. First one says calculate the wavelength of light emitted by a lamp if the frequency is given to you and it's 6.20 times 10 to the 14th hertz. So looking at this problem, we need to figure out what we need to find. Okay, so we need to find the wavelength. So on a pen here. Okay, so we need to find wavelength, which is this guy. We have the frequency, which is V, and that's given to us here. So we're going to use C equals lambda V equation, and we need to solve for the lambda. So that means lambda is C over V if I just divide both sides by V there. Then I just plug things in. So C is always the speed of light, so 3 times 10 to the 8th meters per second is always C. And then our V is 6.20 times 10 to the 14th. Okay, so you take those two, you divide them out, you're looking at about 4.84 times 10 to the negative 7 meters. And that's it. Okay, this next one has another step in here, but it's pretty self-explanatory as well. So purple light has a wavelength, once again, that of this amount right here. Find the frequency, which is V, and then find the energy, which is E. So we need to find two different things here. So that means we need both of these equations. So we have lambda and we know C, so we can find V. Once we have V, we can plug it in here and find E. Okay, so first we need to solve for frequency. C again is always 3 times 10 to the 8th meters per second. Got our wavelength of 4.30. And we calculate. So we divide those out, we're looking at 6.98 times 10 to the 14th. All right, now that we have V, we can solve for energy because E equals hV. H is Planck's constant, which again is always a known value, so H is always 6.626 times 10 to the negative 34th joules times seconds. And then V we just got from right here, so we're going to plug this in, 6.98 times 10 to the 14th, and we just multiply. So we multiply straight through, we're looking at 4.62 10 to the negative 19th and that's it. All right, so you're going to get a chance to practice these problems some more with lesson 1 in the practice packet.